Welcome to Dynamics Laboratory. Today we are going to see how to balance rotating masses if they are revolving in different plane. The aim of the experiment is to balance the rotating masses that are revolving in different plane by finding the angular position of the masses and magnitude of unknown mass. Okay. So we are going to balance the given system by finding the suitable angular positions of the masses, and also we are going to calculate the magnitude of the unknown masses. Okay, this is what the system we have in our laboratory. Here your shaft is positioned by using two bearing. Okay, this is the shaft and we got two bearing at both ends. Okay, the shaft is supported by two bearings. Okay, so here we have masses at different planes. Okay, so this is the plane A, this is a plane B, this is a plane C, and this one is plane D. Okay, and the distance between these planes are provided. Okay, so that is 50 mm. Okay, so each plane is equidistant from one another, so that distance is 50 mm. Okay, here a mass is attached, that is mass A at plane A. Okay, at plane B we have mass mb, at plane C we have mass mc, at plane D we have a mass mt. Okay, so in this problem we are provided with the distance between the individual planes, so that value is given as input data, as well as mass of B, C and D are provided. Okay, so the mass of A is not given. We have to find out the angular positions of these four masses as well as the magnitude of mass A. Okay, mass B, mass C, mass D are provided. Okay, problem description is formulated by using this given data. Okay, so let me read that. A rotating shaft carries four masses A, B, C, D, which revolve at the same radius in planes. Okay, so all these four masses are having same radius. Okay, there is no difference between them. Okay, then the planes in which the masses revolve are spaced 50 mm apart. That is, planes are positioned at equidistance from one another. Okay, and the mass of B, C, D are provided, and they are 188.43 gram, 187.786 gram, 181.656 gram respectively. Okay, find the record mass A and the relative angular settings of the four masses so that the shaft shall be in complete balance. So this is what the problem description. Okay, so the laboratory problem has been slightly modified and it is provided as a problem description. Okay, so that we can easily solve the problem. Now let us see the step-by-step procedure that is required to complete the experiment. The first step is we have to use coupled polygon for determining angular settings of masses B, C and D. And the second stage, what we are going to do is we are going to use force polygon to determine angular settings of mass A and its magnitude. Okay, so we are going to calculate what is mass A and its angular position. Okay, and third, we are going to use these results, and based on that we are going to align the masses in the shaft system. Okay, so in the experimental setup, okay, we are going to align the masses based on the angular settings that what we have calculated through graphical calculations. Finally, we are going to run the rotor shaft system to verify whether the shaft is balanced or not. Okay, so we are going to rotate this shaft to a certain level. Okay, so we are going to gradually increase its speed to certain limit until we observe some vibration. Okay, so once we started observing certain vibration and noise in the system, we are going to record the corresponding speed. Okay, so we are going to calculate what could be the maximum speed up to which we can operate the given system. Okay, so that it will not vibrate due to unbalance. Okay, so though we have calculated the suitable mass as well as its angular settings so that the system can be in complete balance, so there will be a slight calculations error, settings error may be present in the system. So definitely when it crosses certain speed, it will start to vibrate. Okay. So we are going to calculate what is the maximum speed at which the system can be operated without any vibration. So this is the procedure that we are going to follow. Okay. So now I'm just going to use that position of plane of masses for our experimental study. Okay. So for that we are going to draw the couple polygon as well as force polygon. For that we need to have a position of masses. Okay. So here this is the representation of the given system. Okay. So here you can see that this is the position of masses. I'm just going to represent this diagram as a representation diagram. Okay, so here you can see that this is the position of masses for our given case. Okay, so that is each plane is equidistant from one another, that is 50 mm. So here I am just going to take A as reference because I'm just going to calculate the mass of A. So it is better to consider A plane as our reference. Okay, so that we will get three known value in a couple polygon. Okay, and from that I can calculate their angular settings, and while drawing force polygon I can calculate what is the mass of A. So it is better to choose A as our reference plane because A value is unknown. Okay, and this distance of 50 mm, so I'm just going to take A as reference. So all those planes are just positioned with respect to A. So, okay, it is 50 mm and C is located 100 mm from A and D is located at 150 mm from A. Okay, and this is the centrifugal force and couple calculations. Okay, so we have got four different planes and masses are provided. Okay, and all those values I just converted that into kilogram. Okay, so values are given in gram, we have to convert those things into kilogram. Okay, so mass of A is not provided and other values are given. Okay, as far as radius is concerned, so we don't need to bother about these things because they are revolving with same radius. Okay, so in these calculations we are not going to consider the radius value. Okay, so that is why while calculating the centrifugal force, so we know that what is centrifugal force, that is mr omega square. So while calculating centrifugal force, r is common and omega is also common. So we are going to ignore these two values in this calculation. So we are going to consider only the m value. Okay, so the reason is r value as well as omega values are common, that is same value. Okay, so we know that y omega value is common one or the same value. The reason is though we have got four different masses which are revolving in different planes, they are attached to a same shaft. So the omega value will be same for the all the masses. Okay, fine. So we are going to ignore r and omega value. So finally we are going to get only m here. Okay, so the centrifugal force is exactly equal to the value of m. Okay, so now distance from reference plane A. So we have taken A as our reference plane. So we have to take the distance of other planes with respect to A. Okay, so as far as this plane is concerned, it is 0 because it is a reference plane. Okay, so B is located at a distance of 0.05 meter from A, and this C is located 0.1 meter from A, and this D is located 0.15 meter from A. Okay. Now let us find out the couple value. Okay, so we know that couple value is mr omega square L. Okay, in which r is common, omega square is common. So we are going to remove these two things and we are going to only calculate this value m L. Okay, mass multiplied by this distance. Okay, so we are going to multiply this with this distance. Okay, so here since it's a reference plane there is no distance, so the couple value is going to be 0. For B it is 0.009421, for C it is 0.018778, and for D it is 0.027248. As far as the angular position of these masses is concerned, we don't know exactly their values. Okay, So we are going to calculate these values. But for solving this problem, we are going to take B as 0. Okay, so because I'm just going to consider this mass B like this. Okay, that is, it is going to be located in the horizontal direction. Okay, so it is going to be 0 value. For other three masses, we have to calculate their exact angular positions. Okay, from this table, we can easily realize that whether we can proceed with the centrifugal force polygon or with the coupled polygon. So in the coupled polygon, we have got three value, one value becomes 0, so we have got three value, and for direction is concerned, we know the direction of plane B because it is going to be located horizontally. Okay, so we have to start from drawing coupled polygon. Okay, so if I start from a force polygon, then I cannot complete the problem. So we have to understand that it is easy to complete the problem by starting from drawing couple polygon. Okay, now let us see how to draw the couple polygon. Okay, as far as angular position is concerned, we only got the angular position of mass B. Okay, that is, it is going to be located horizontally. For other masses, we don't know exactly the angular positions, so that is what our task. We are going to calculate it by drawing this coupled polygon. Okay, so this is the scale that I have just taken to construct this coupled polygon. So 1 kilogram meter in this coupled polygon is going to represent 400 centimeter. Okay, fine. So now first let us take that coupled value for the mass B. Okay, so it is going to be located horizontally. Okay, and this is O dash, A dash, and its direction is very clear. It is positive and it is radially outward direction. Okay, and its magnitude is 0.009421. Okay, now how much distance that I have to measure in my actual scale while constructing this coupled polygon? So that you need to decide based on the scale value. So 1 kilogram meter represents 400 centimeter. So this 0.009421 kilogram meter represent exactly 3.7684 centimeter. Okay, so for constructing this diagram, we need to use the scale so that we can construct that precisely. Okay, so we cannot just take 0.009. Okay, that is why we have to convert that into proper scale so that we can draw this diagram without any mistake. Okay, so in actual scale, we need to take 3.7684 centimeter because 1 kilogram meter represents 400 centimeter. Fine. So now I have completed this side. Okay, so just one side of the polygon is completed. We have represented this couple here. Okay, so now how to draw the sides of that couple polygon, okay, which represents the couple of mass C, mass D. Okay, I don't know exactly their direction, so but I know their magnitude. Okay, so what I'm going to do is I'm going to take these values and I'm going to use compass. After taking this measurement, I'm just going to make an arc here. Okay, so first I'm going to take this value, that is 0.018778, and I'm just going to make an arc from A dash. And for this D, I'm going to take this value compass and I'm just going to make an arc from O dash. By joining this, okay, I get a line. Okay, and this distance is 0.018778, but in actual scale I have taken the value is 7.5112 centimeter because 1 kilogram meter represents 400 centimeter. Okay, so to find out this exact value, so what you need to do is you need to multiply this value, that is 0.018778, with this 400, then you will get this value. So the value we have to take in actual scale. Okay, then by connecting these 2 points, I can get the direction of this mass D, and its magnitude is already known, and the actual scale I have just taken to make an arc here is 10.8992 centimeter. Okay, so now the coupled polygon is completed. So from that, I'm going to take the angular positions of mass C and mass D. How to take those values? So this represents the direction of a couple of mass C. Okay, so I have measured this angle from horizontal. So it is 33.5 degree. Okay. So here I'm just going to represent the same direction for MC. Okay. So this is the direction, the parallel line I have constructed here, and this angle is 33.5 degree. Okay. And now let us come to this part, that is mass D. This is the coupled direction of mass D. So I'm going to draw the horizontal line, and I have measured this angle as 204 degree. Okay. So I'm going to represent this couple in the angular position. So I'm going to draw a parallel line to that to represent mass D, and this angle is 204 degree. Okay. The only one force direction which remain unknown is A. Okay. So that we will calculate by drawing force polygon. Okay. So now let us see the outputs that what we have just got from this coupled polygon. Okay. So from this force polygon, we have got that theta C is 33.5 degree and theta D is 204 degree. Okay. So now let us see how to construct the force polygon. Okay, because we need to calculate the value of mass A and its angular settings. Okay, so I'm just going to use that same angular position of masses. Okay, we have determined the angular settings of MC as well as MD, and this is what the centrifugal forces. So these are all the things are required for us to construct the force polygon. Okay, so first force is this one. So MP corresponding value is 0.18843. Okay, so in order to represent this value, I'm going to take a scale of 1 kilogram, which represents 40 centimeters. I need to multiply this value with this 40 centimeter so that I can get the value that I have to take in my scale. Okay, the first force is 0.18843. Okay, so the direction is here and its magnitude is 0.18843. Okay, and in actual scale I have just taken 7.5372 centimeter. Okay, and the second force is 0.187786, which represents mass C, and its direction is here. So I have constructed a parallel line to this direction to represent the forces which are corresponding to mass C, and it is 0.187786, and the actual value which I have taken scale is 7.51144 centimeter. Okay, so now let us consider this mass B. Its direction is here, so I'm going to construct a parallel line to that with a magnitude of 0.181656. In actual value I have taken 7.51144 centimeter. Okay, so now you can just think of that. Okay, because the force polygon is not closed, but we have got another value which remain unknown, that is the MA value. So the closing side is exactly equal to this value MA. Okay, so this is the closing side. Okay, and the direction must be also taken in the same order. Okay, now we can easily calculate its magnitude by measuring this length, as well as its direction can also be easily found. Okay, so this is the horizontal line which I have drawn. Okay, from that I have measured these positions, which is 190 degree from horizontal. So I have represented this position in the angular position of masses. So here the angular distance is 190 degree from the horizontal. Okay, so now let us see how to calculate the magnitude of ME. Okay, from force polygon I can measure this distance CO. Okay, so which is equal to 7.81 centimeter. Okay, so by dividing it with 40, because it is in centimeter, so I need to convert that into kilogram. It is 0.19528 kilogram. Okay, so the mass A is 0.19528 kilogram. Okay, so this experiment we have calculated what is the unknown mass A, and we can convert that into gram. Okay, and angular settings of masses A, B, C, D, so that the shaft shall be in complete balance. Okay. Here you can just see that how these masses are aligned based on our calculation. So one by one we have to add these masses to the shaft by taking the exact angular position using this scale. Okay. This angular settings arrangement will help us to position these masses exactly at the positions that what we have calculated. Okay, and as far as the distance is concerned, each plane is located 50 mm from one another. Okay, equidistant from one another. Okay, we are going to put this second mass at exactly 50 mm from this first mass. Okay, and also we have to make sure that exactly the angles are referred from the horizontal. Okay, so now you can just see that these four masses are aligned based on that angular settings that what we have calculated. Okay, and the distance also exactly positioned based on the given case. Okay, here you can just see a motor. It is used to drive the shaft system, and it is connected through a belt drive. Once the arrangements were made, we can rotate at higher RPM by changing its voltage of that motor, and we can use a digital tachometer to find out what is that exact speed at which that shaft is rotating. And visually, we are going to observe whether any vibration and noise is there in the system. Okay, so we are going to gradually increase the speed until we reach a point that where we feel a mild vibration and noise in the system. Okay, so whenever if we start to observe that any vibration or any noise in the system, so we are going to measure that speed of the shaft using a tachometer, so that we can say that up to this speed this balance system can be operated. Okay, so you can just think of that it is completely balanced. Okay, so we have done a calculations and we have exactly positioned based on that angular settings, but anyhow there may be some manual error will be there in calculation, there will be minor error will be there, and also while setting up this masses there may be some error. Okay, so we cannot say that it is completely balanced, perfectly balanced. Okay, it is balanced to some extent that it can be operated up to this speed. Okay, this is what the conclusion that we can say by doing this experiment. Okay.